Welcome back to The Explainer. Today we're diving straight into episode 5.2, Measurement of Power and Energy, and we're really focusing on watching the whole load picture. Now think about a scenario that literally plays out in industrial plants every single day. A motor on your floor could be drawing perfectly normal-looking current, humming along without triggering a single overcurrent alarm, and yet, it could secretly be wasting your money and slowly melting your cables. Crazy, right? But how is that possible? Well, it's because there's this entirely hidden layer to power consumption that basic current monitoring just completely misses.
You know, you might glance at a simple ammeter reading and think, hey, everything looks perfectly fine. But that current reading, it's really only telling you a fraction of the story. You simply cannot see the hidden strain of a poor power factor from a basic current measurement alone. To understand what is actually happening in your electrical network, to see exactly where the stress is and where the money is going, you absolutely need the full power and energy picture.
So to grasp this full picture, we really need to separate power into its true components. Think of it as useful work versus overhead. Active power is the actual useful work being consumed. It's the energy that turns the motor shaft, pumps the water, or moves the conveyor belt. Reactive power, on the other hand, well, that's your overhead. It is completely necessary to support the magnetic fields and inductive loads like motors and transformers, but it does absolutely zero useful work itself.
To kind of ground this abstract electrical theory, think of a simple trip to the supermarket. It's a great analogy. Your electrical system is just like pushing a grocery cart. Your apparent power is the total volume of your cart, basically how much physical stuff you're pushing around. Your active power represents the actual useful groceries you're eventually going to eat. And the reactive power, that is the bulky, mostly empty packaging taking up space in the cart. So, a low power factor essentially means your cart is mostly useless packaging. It's taking up valuable space and making the cart heavy to push without actually feeding anyone.
And this brings up a massive misconception in our industry, equating current draw directly with power consumption. A poor power factor actually forces a motor to draw significantly more current than its useful output suggests. If your cart is full of packaging, you're straining your arms pushing it, but you don't have much real food to show for it. In your plant, this means you are pulling massive amounts of current, literally straining your cables and your transformers, without getting proportionately more useful mechanical work out of your machines.
All right, let's move from the grocery aisle to the actual physics of the network. This relationship forms what we call the power triangle. It shows the precise geometric relationship between your useful work, your overhead, and your total power. Active power, denoted as P, forms the horizontal leg of the triangle. Reactive power, Q, is the vertical leg. Apparent power, S, is the hypotenuse. That's the longest side connecting them. And the power factor, or PF, is the angle between the useful work and the total apparent power. The larger your reactive power overhead gets, the wider that angle becomes, and the longer that apparent power line gets. Mathematically, this all ties together through some core formulas. Active power, P, is measured in kilowatts. Reactive power, Q, is measured in kilovolt amperes reactive, or kVAR. To find your total apparent power, S, which is measured in kVA, you simply take the square root of P squared plus Q squared. Finally, your power factor is just the ratio of your active power to your apparent power. It's a dimensionless number, sitting right between 0 and 1, that tells you exactly how efficiently your system is utilizing the power it draws.
So how on earth do we actually track all these complex metrics reliably in a live, active industrial environment? Well, that is where advanced relays like the ABB RET615 Transformer Protection and Control Relay come into play. Hidden inside the specific device is a highly specialized piece of software logic called the PEM-MXU function block. This power and energy measurement block acts as your primary technical tool to continuously monitor and calculate all of these metrics in real time. The PEM-MXU function provides incredibly comprehensive load profiling. It's outputting active power, reactive power, power factor, and your cumulative energy consumption. But how exactly does it do this? Well, it continuously measures both the magnitude and the precise phase relationship between the incoming voltage and current waveforms. By analyzing that phase angle, it mathematically separates the useful in-phase current component from the non-useful out-of-phase component. It basically gives you the full, unvarnished truth about what your motor feeder or capacitor bank is actually doing under the hood.
And what makes this block so incredibly valuable is its sheer precision. The PEM-MXU block boasts an operation accuracy of plus or minus 1.5% for active, reactive, and apparent power. We are not talking about a rough estimate or a ballpark figure here. This is highly precise data.
When you're trying to assess how efficiently a motor feeder is using supplied power or identifying tricky load imbalances, you need data you can absolutely trust to make solid engineering decisions.
Okay, time for a quick, real-world check to see this in action. Imagine you're looking at a motor feeder that shows 80 kilowatts of active power being consumed, and it has a power factor of 0.8. Using the formula we covered just a minute ago, where apparent power equals active power divided by the power factor, what is the approximate apparent power, or S, of this system?
If you guessed 100 kVA, you hit the nail on the head. But seriously, think about that for a second. The actual muscle the motor provides to your process is only 80 kilowatts. But because of that 0.8 power factor, the system has to draw a total apparent power of 100 kVA. That is a massive jump from the active power number, and it really puts the inefficiency of a poor power factor into perspective.
Now, why does this 100 kVA jump matter so much to us as electrical designers? It matters immensely because physics simply doesn't care about the useful part. It only cares about the total. Your cables, your transformers, and your upstream protective devices must be physically sized to carry that full 100 kVA of apparent power. If you mistakenly sized your infrastructure based only on those 80 kilowatts of useful active power, your equipment would be dangerously undersized and at serious risk of overheating or catastrophic failure.
And this is exactly why poor power factor isn't just some abstract mathematical theory. It brings tangible, highly expensive consequences to your plant. It creates very real I²R heat losses in your cables, physically degrading the insulation over time. It forces you to invest heavily in oversized infrastructure just to handle that reactive overhead. And furthermore, it can trigger massive utility power factor penalty charges on your monthly bill. You are quite literally paying heavily for capacity you aren't even using for production.
Which brings us to a final really critical thought for you to consider today. What hidden drains are quietly straining your network right now? And more importantly, is your relay actually programmed to catch them? Remember, combining precise PM/XU power data with the kind of thermal monitoring we often discuss gives you the ultimate, complete picture of your electrical system's health. Do not let your network run blind on just a basic current reading. Thanks so much for joining this explainer, and we will see you next time.